Our last but not least talk is by Mike Taylor, definitely. And he's going to talk about a new airglow measurement technique about which I am very excited and I think offers us all kinds of interesting possibilities. Let me.
Well, Colin, I hope you can hear us. This is great to be bringing up the rear in this talk, and really delighted to have the opportunity to present some work on all stimulated by your original studies. And just to move forward, atmospheric imaging studies, which I'm going to focus on now for the rest of the talk, was really stimulated by Colin's paper where he talked about waves in the upper atmosphere in meteor signatures and in noctilucent clouds. But there was a tremendous breakthrough about 10 years after Colin's seminal paper with infrared photography. Infrared film became available, and people started to experiment by pointing cameras with infrared film, taking long exposures, looking at the low elevation, and they saw structures there. So these structures, as you see, there are elongated features. This is by Peterson and Kefauver 1973. And then Mariels and Hersey, you see a panoramic. They started to use more than one imager and things like that. So immediately started to see that the sky was full of these waves, and this was a capability of being able to study them at any latitude and any time of year, unlike with noctilucent clouds when you're limited to the summertime at high latitudes. That, of course, led to lots of nice discoveries, and I just put a few examples on here and a little bit of advertising, sorry. This is my PhD work a long time ago. Circular gravity waves, excellent studies then when Gary started working with all-sky imaging. This is now waves over, it's from the Aloha campaigns, over nearly 500,000 square kilometers, and some stuff we also did with mesospheric Bohr events, these sharp features. Some beautiful evidence of wave breaking events and by the Japanese Yamada, it's a famous Yamada event it's called. And we're going to talk a bit more about today imaging rather than all interested in intensity, but in temperature as well. So that came along with instrument developments, and I call this evolution of airglow images, but really evolution of me. And so this is what the camera used to look like. You know, this is a good old TV camera. The tube in there was about 3 foot long, and I used to hand carry it through security. Can you imagine trying to do that now? It looked like a bazooka. Anyway, this one now looks like a bazooka too. But essentially, obviously, they've evolved a lot. The CCD instrument has become a fantastic device for multi-wavelength measurements of emissions in the airglow layers, several airglow layers in the mesosphere and in the thermosphere, of course. But the ones that we use a lot is the OH layer, about 87 kilometers. And this is Jim Hecht and I, we've both been working with temperature mappers in the 90s, and we've now been what we call an advanced temperature mapper, where we're using more in the deeper red. Jim now also uses the deeper infrared, and we're basically looking at emission lines in the OH31 band, which gives us a very strong signal, about 75 times the signal you would get from a CCD, and you can then get temperature measurements with a precision of 1K in less than 30 seconds. So there's a lot you can be done. And the nice thing is these emission lines we use now avoid the aurora, so we can now do these things at high latitude in the winter. So we go to beautiful places like Alamaar in Norway. We have a collaborative program with Dave, and there's Dave Fritz, and there's a sodium LiDAR, and there's a meteor radar, several sorts of different radars, so we're getting wind and wave data. So I just click on this thing, Dave. Right, here, well, it's going to be a movie, hopefully. Well, that clicked. Go back and click. All right, yeah, I'm getting educated. There you go. It likes me. Okay, so this is a temperature mapping image about from 200 to 230 Kelvin. You're seeing waves moving through the field of view. This is not an unusual night. We see this fine structure with temperature amplitudes around a few to several Kelvin all the time. But as you're seeing, this obviously speeded up. This is about 4 hours worth of data. You're seeing all these fine scale features and superimposed larger scale features, and you'll see some nice coherent stuff coming through. And then the background's changing all the time because you're really superimposed on tidal features and other things going on. So anyway, that went quickly, but we'll just move on. As Gary referred to, there are other ways of just looking at the structure within the images, and he's pioneered the Auroral Keogram for airglow studies. And you just take slices vertically and horizontally through the pictures, and you can build up stacks of these things. So you get a time series over a large field of view that you can look at. And this is the way you can actually look at larger scale waves. This is the same night I just showed you the movie for. The movie was this duration here, but the night is obviously a lot longer. And you can see periodic features in the intensity. We get a north-south and an east-west Keogram in intensity and in temperature. And so the temperature data corresponds here. So with this instrument, you're getting temperature perturbations, intensity perturbations, you're getting wave periods. With the background winds, you can get the intrinsic frequencies. All of the information is there for doing momentum studies and things like that. So it's opened the door to all of this with a tight set of instruments. And you can see periodicities of around about an hour here and superposed waves, so you can see the interaction of the waves. And sometimes you see breaking wave events and various instability features that Jim does a lot of studies on. But I'd like to talk about one breaking event now, as observed from Alomar. This is about 40 minutes, the event lasted about 40 minutes. It entered our field of view, it's just bottom corner here, moved fairly rapidly across the field of view, and there's some aurora around earlier and things like that. But you can see as it starts to exit the field of view, it starts to, if you look, like shedding waves, and then it's breaking and becoming quite turbulent in the last 15 minutes. The reason that this is of interest is that it's possible evidence, as Brian referred to, of a self-acceleration event, because it was already, when it came into the field of view, it was moving around about 80 meters a second. But when we measured the observed phase speed, I've got phase speed plotted here versus times, so over a period of about 30 minutes, the phase speed went from about 80 meters a second up to 120, so it's increased by 30 meters per second there. And we don't get measurements every 5 minutes. You can see lots of dots there. We get measurements every 30 seconds, so this is a highly sort of a well-sampled event. If you look at, we have background wind measurements from the Auroral radar, and you can actually then determine the intrinsic phase speed, and you see it's roughly constant. It started to dip a little bit later. But that's all happening while the wave, we don't have measurements of its velocity when it's breaking, because it's all falling apart, if you like. But you can see, so it's evidence of a wave growing in speed. But as Brian talked about, associated with this, we should see a sudden change in the background winds, and that's exactly what happened. So it's the Auroral winds radar data from, up at Alomar, and you can see at the time of the event, which is indicated by these arrows, there was a large change in the meridional and the zonal winds, so large, and it occurred at about the altitude I've indicated here, the mean altitude of the OH layer, and above. So it looks like, as we see in the plots shown here at half-an-hour intervals, this is the region when the wave's breaking. You can see these ones that show these are before the wave broke, and then this is where it's entering our field of view and breaking. We're getting a large increase in the background winds. So that's sort of two things. And then the next one was, as Dave talked about in his talk, was you get this apparent 2D instability. It's just parallel features, but they start to, with the high temporal resonance, you can see them oscillate and then start to whirl and break up as you go through into 3D type stabilities. And I have another event this afternoon I'd like to show you in the Jonathan Snively's session, where we see some even finer detail in an event over Utah recently. So if I wanted to summarize that, we got the large mean wind flow acceleration, corresponding increase in the background gravity wave phase speeds. Say the intrinsic phase speed stayed roughly constant, and then you have these 2D evolving into 3D instabilities. So it's possible evidence, as I said, new evidence for a self-accelerating event. And just to finish off, I want to show you something that's, as Colin said, you want to be challenged by the data, and he actually left. I didn't know he left the field and then came back when he found out there were other things to challenge him. So I wanted to show you this movie as a challenge for, come on, speak to me. There you go. Same format, 180 by 140 kilometer field of view. So it's taken over Utah last year, and I'm just showing you the dynamics that are going on here. It's about 5 hours worth of data being you're going through very quickly, but you can see all these overturning features. We don't see this all the time, but we do see this quite often now with this system. It's a very dynamic atmosphere that we have, and that's where I'd like to stop so you can have some lunch. And thanks, Colin.
Great job, Mike. Nice and concise. Any questions before we leave?
What's for lunch?
Everybody's hungry?
No worries.
So thanks for wrapping up what I think was a great session. Thank you to all of the speakers. Thank you, Colin, very much for joining us for this. I'm sorry that you weren't able to see things more completely, I think, but we'll be happy to provide as much detail as you would like thereafter. So thanks, everybody.
Yeah. Thank you, Colin.
Thanks to you, Dave, and Mike, and all the other speakers. I have one comment to make. At my age, I'm looking at grandchildren and potential great-grandchildren, but it struck me that there's an analogy to be made with starting a family and writing what turns out to be a seminal paper. You just don't know where it's going to go from the start. But it's wonderful stuff that's coming along now. I'm looking forward to seeing the tape.
Well,
thanks very much.
Thank you, and you've planted some great seeds with us, and we're trying to carry it forward.
Great.
Thanks also to David for helping us set up on that end.
Thank you.